Welcome to the CopperSpice YouTube channel, and thanks for joining us. This video is going to show how Lambda expressions and function objects can be used to implement a callback. Lambdas in action. We have talked about Lambda expressions several times, and it occurred to us that some of our definitions could use further refinement. Our objective in this video is to provide a clear delineation between Lambda expressions, std function, and function objects. We are going to show two detailed examples illustrating how a Lambda expression is a very clean way to implement a callback mechanism, and how to store one so a different function can invoke it.
We would like to start with a brief review of the Lambda expression syntax. Programmers tend to use the term lambda as an abbreviation for a Lambda expression. The C++ standard only uses and defines the term Lambda expression, so we encourage everyone to use the full term for accuracy. We feel strongly about this because it really is an expression. As shown in our example, the data on the right is assigned to a variable. Since a Lambda expression returns a compiler-dependent data type, this variable should usually be declared with auto. The syntax for a Lambda expression is very precise. There are three main clauses, delimited by square brackets, parentheses, and curly braces, and they must be in that order. The parentheses can be omitted if the parameter list is empty, but this is usually not the best idea since it reduces readability. The first part of the Lambda expression is the capture clause. This specifies which outside variables will be available inside the body of the Lambda. It is not necessary to capture any data, however the square brackets are always required. Next comes the parameter list, which is very similar to the parameter list for a normal function. This can be followed by an arrow and a data type. This data type declares what the Lambda expression will return when invoked. Normally this can be deduced, so no return type is required. The last portion is the Lambda expression body, which is enclosed in curly braces and has the same purpose as any other function body. One other issue we want to mention is the tendency for developers to use the terms closure and Lambda expression interchangeably. In C++, a Lambda expression is only considered a closure when there is something in the capture clause. A callback is a computer science term for a function which is invoked by some other function. The calling function can be written without having any idea or even caring what the callback will implement. It is perfectly valid for the callback to simply return and do nothing. The power of a callback is that the calling function can take the information about which callback to invoke as a pass parameter. In many languages, this parameter will be implemented as a function pointer. C++ allows us to implement a callback using a Lambda expression. In the following examples, we will show how this is accomplished and the power of being able to encapsulate a callback function inside of a Lambda expression. Before we talk in detail about how to use a Lambda expression as a callback, there are a few other terms we need to review. Sadly, these terms sound very similar, and they are often used interchangeably, when in fact they are not the same. This can make communication difficult and lead to design flaws due to misunderstandings. The first term we want to talk about is function pointer, which is a specific kind of pointer. It is a pointer which refers to a function rather than a particular piece of data. Many languages have some kind of function pointer type, and the one used in C++ has its roots in C. A normal pointer holds the address of an object. More accurately, a pointer references an L value. A function pointer is a bit different since it refers to a particular free function. It may be surprising to hear, but the term functor is never used in the C++ standard. Many C++ programmers still use it. However, since it has no defined meaning, you might want to steer clear of this term. Most often when C++ programmers say functor, what they are actually referring to as a function object. There are times when someone does mean the term functor as defined in mathematical category theory. However, this is rare in C++. A function object is a class which declares an operator parens method, often referred to as the function call operator. This allows an instance of the class to be called as if it were a function. Before the release of C++11, creating a function object had to be done manually, and it was a bit messy. While this option is still available and is useful if you have some unusual requirements, generally it is preferred to use a Lambda expression which produces a function object, rather than writing the code for a function object directly. The last term we want to discuss is the templated class stdfunction. It is often confused with function objects or function pointers. The difference is that stdfunction is a container class, which holds a single function object of the desired signature. One of the main reasons stdfunction was added in C++11 was to store a Lambda expression. Without this class, storing a Lambda expression in a data structure would be painful and hard to do. It is worth noting you can also store a function pointer or a handwritten function object in stdfunction.
So let's look at a real example where we use a function object as a callback. Suppose we have a media player, and the user interface has a slider and a numeric value to indicate the current playback position in the audio file. It would be nice to update the user interface at some regular interval as a background process. The first step is to set up a timer, which will trigger once per second. We also need a method which is called every time the audio changes state. When the media starts, we want to add a new callback. Otherwise, we want to remove the corresponding callback. These two methods are called AddCallback and RemoveCallback. The implementation of AddCallback is where the actual callback function object is created. Next, we set up a signal slot connection. The timer is the signal, and when the interval elapses, a method in our media object is automatically called. This is the method which is responsible for actually invoking the callback. In this code, we are only showing the relevant parts of the media constructor. The timer will be created, and the interval is set to 1 second in the constructor. The purpose of the stateChanged method is to decide if we need to add a new callback or remove an existing one. When the user switches between the modes, the stateChanged method will be called with an argument indicating the new state. The position property holds an integer value indicating where we are in the audio file. Note that when we call the AddCallback method, we pass a template parameter of int. This allows us to specify the data type associated with the position property. The code in the AddCallback method is the interesting part. The goal is to create function objects and then capture them in a Lambda expression. We are not invoking the function objects in this method, but rather storing them in the closure so they can be invoked later on. The first thing we need is to obtain the meta object for the QMedia class. The meta object is a class which provides functionality to look up properties by name at runtime. The read property is a method of the meta object, and in this example, it returns a function object, so we can assign it to a variable with a data type of stdfunction. The template parameter indicates the return type and argument types for the function object it is storing. For this read method, the return type t is int. This is based on the template parameter which was passed to AddCallback. Since there are no parameters which need to be passed when we eventually invoke read method, the argument list is empty. The signal method is set up in much the same way. The function object saved in signal method will be used to emit a notification that the position in the media player has changed. The application can react to this signal and update the user interface with the new position value. In the capture clause of the Lambda expression, we must list the variable names from the outer scope, which will be used within the body of the Lambda expression. In this example, we need to capture read method and signal method. In the last line, the new callback is passed to the AddWatch method. This code illustrates the value of encapsulation. The closure has no knowledge of which properties are being watched, since the body of the Lambda expression is just two function calls.
The purpose of the AddWatch method is to store the new callback in a map. The property name will be used for the key. This provides a convenient way to erase the callback from the removeCallback method. The value is where we store the std function, which contains the callback. Since std function is a template, we must specify the callback signature in the declaration of the map value and the AddWatch parameter list. It is important to reiterate that this signature indicates what data type the callback will return, and what, if any, parameters are passed to the callback. This particular signature is unrelated to the signatures for the function objects used inside the body of our callback. AddWatch checks to see if the timer is active. If not, we connect the timeout signal to our TimeUp method and start the timer. Although everything in this method could have been part of the AddCallback method, we decided to do the last few steps in a separate method. Since AddCallback is a template, it must be located in the header file. The AddWatch method is not a template, so it can be in the source file, which reduces binary size. The TimeUp method is automatically called when the timer interval is reached, which occurs once per second. This method simply loops through the entire map and invokes every callback, which could be for several different media properties. Notice that this method does not contain any information about the property name or what to do when a property value changes. We have successfully hidden the implementation in the Lambda expression, which was created long before it was invoked.
In this second example, our goal is simply to update the screen with information about the selected audio track. It would be nice to populate the playlist with information like the title of the song, the artist, and the duration. This is far more useful than showing a URL or a long and hard-to-read file name. The problem is that the metadata may not be available right away, since the media player needs to load the file to provide this information. It is not practical to just sit and wait for the data to be available, since it would make the program unresponsive. Instead, we are going to set up a signal slot connection where the slot is a Lambda expression, which retrieves the metadata and updates the screen. So we start by doing a bit of setup. First, we convert the selected file name to a URL, and then create an empty temporary media object. Then we set up the connection from the media object, which will send a signal when the internal metadata change event occurs. When this signal happens, our Lambda expression will be invoked. The last step is to call the setMedia method to instruct the media player to load the audio file. The connect method is part of the signal slot system available in the CS signal library. Similar techniques would also work by using the Boost Signals 2 library. We create the URL from the user-selected audio file name. Then we create the temporary QMedia player instance using a shared pointer. The purpose of the connect method is to set up what the program should do when the signal event happens. The spot where we have the 2 question marks is typically a method pointer. In this case, we are going to write a Lambda expression. Our Lambda expression needs to capture the temporary media player and the URL. In the body of the Lambda expression, we set up default values for the title and the artist, just in case the media metadata is not successfully loaded or available. This might happen if the file is corrupted or has no metadata tags. Before we call the metadata method, it is important to make sure the data is really available. If it is, we go ahead and retrieve the values. Whatever code is required to update the screen can be added at the end of this Lambda.
This is the entire code for setting up the temporary media object, creating the connection, and then calling the setMedia method to load the audio file. It is very important to do these operations in this exact order. We must ensure the media player does not load the file before we have set up our connection and the Lambda expression. If you try to call setMedia too soon, it might load the file so fast that you will miss the metadata changed event. Although Lambda expressions and std function have been around since C++11, many programmers tend to use them in somewhat basic ways. We hope that through these examples, you have seen how a Lambda expression can be used as a callback to encapsulate data in a function object and then stored in an std function. For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back in a few weeks for our next video.